We're going to continue looking at uniform circular motion, but now we're going to change directions. We're going to look at something swung in a vertical circle. And this is actually pretty common. When you have hills undulating on a highway, that's a vertical circular motion, sort of. When you have a roller coaster that has a vertical loop, we have the uniform vertical motion. So we're going to look at those in a variety of ways, but we're going to start simple. We're going to start with an object swung on the end of a string. Now, there are a couple things you want to keep in mind when we're dealing with vertical uniform circular motion. First, we're still talking about an object moving with a constant speed, or we're talking about an instant in time where it has a speed. Okay? The radius of the circle is not changing, or we're looking at one instance of it where the radius is known. Okay? The only acceleration is centripetal acceleration. So when we're looking at it, when there's only centripetal acceleration, that means the only force acting on it, or the net force, sorry, the sum of the forces, is going to be the centripetal force. However, there will be more than one force acting, and we're interested in those and how they're interacting. Okay? And so probably the easiest way to illustrate this is to consider an object that you're swinging in a circle in front of you, right? But instead of swinging it over your head, you're swinging it in a circle vertically in front of you. Now, it still has a radius r, and I'm going to go ahead and we're going to let the radius be 0.75 meters. And it still swings around in a circle, so it's going this way, and I'm going to let it be going with a velocity 5 meters per second. Okay. And the object, we'll even leave it with the mass we had before of 300 grams or 0.3 kilograms. Okay. Now, if you look at this, since the speed is constant, the acceleration is centripetal acceleration. Okay, that's the only thing that's going on. But if we look at it right here at this point, there are two forces acting on it. There's the force due to gravity, Fg, pulling down, and there is tension in the string, Ft, and that has to be directed towards the center because the net force is the centripetal force, and remember, centripetal force is always directed towards the center. So a lot of times when we're dealing with circular motion, we make positive, the positive direction is towards the center because the centripetal acceleration is towards the center. So that means when I set up my frame of reference, I set it up so that towards the center is positive. Alright, so the net force is Fc. And if we're looking at the bottom of this thing, then at the bottom, Fc is the sum of these two forces, but really tension is positive because it's towards the center, and the force due to gravity is negative because it's down. So I went ahead and subtracted that, and that is going to be mass times acceleration. But since our net force is just the centripetal force, that is centripetal acceleration. So if I want to know the tension in the string at the bottom, I can see that the tension at the bottom is going to be equal to mass times centripetal acceleration, that's the force required to put it in circular motion, plus Fg, that's the force required to hold it up against gravity, right? If this thing was at rest down here and it wasn't spinning, then the tension force would be equal to gravity. But since it is spinning, we have to add on that extra little bit that makes it rotate. Okay? And we can actually go ahead and do that. So mass is 0.3 v squared over r, so v is 5 squared divided by the radius, 0.75. So 25 times 0.3 divided by, okay, so that's 10, plus the force due to gravity, 0.3 times 9.8, and this is 2.94. Okay, so I have a tension over here when this thing's at the bottom of the circle of 2.94 newtons, or sorry, 12.94 newtons. Now, let's go to the top. Okay? So I'm actually going to start with a new picture so that we can see the forces labeled the other way. So here's the object right here at the top, and remember the mass is still 0.3 kilograms, the velocity is still 5 meters per second, and the radius is still 0.75 meters. Now, when we're here, the string is pulling towards the center still, so I have this force, this is the tension in the string, and then I also have the force due to gravity. It still pulls down, so those two forces now are going in the same direction. So now when I find the net force is Fg plus Ft, and that has to equal the centripetal force, which of course is m times centripetal acceleration. So Fg is still mg, Ft is whatever Ft is, and this equals the centripetal force, mv squared over r. So now when I find Ft, I can see that Ft is going to be equal to mg Ft is going to be equal to mv squared over r, or the centripetal force, minus mg, the force due to gravity. Because gravity is supplying some of the force required to spin it in a circle, we don't have to pull quite as hard on the string. Now, if I find this, we're going to see that Ft equals 0.3 times 25 divided by 0.75 minus 0.3 times 9.8. So this time I have 10 minus 2.94, which is 7.06 newtons. So at the top of the swing, the tension is less than at the bottom of the swing because tension has switched directions. Because gravity is fighting us here. Gravity wants this thing to come down and we're trying to swing it up. But at the top, gravity's helping us. We're trying to swing it down and gravity's trying to pull it down. So because we have vertical motion and gravity is constant, but our centripetal force is always towards the center, we have to account for that. Now, if we were to look at it right here, it wouldn't matter at all because that force is at a right angle to this force and they would be independent of each other. Okay, so this one's actually in the direction of the velocity. Okay, so the top and bottom of a circle are oftentimes where we're interested in finding tensions and forces in the vertical direction.